Welcome everyone to the Bioengineering seminar series, and today we've got Abdon Pena-Francesch here with us. He's an assistant professor in material science and engineering, macromolecular science and engineering and robotics at the University of Michigan Ann Arbor. And he obtained his PhD from Penn State University and his bachelor's and master's from the Chemical Institute of Sarria in Barcelona. And he was also a Humboldt postdoctoral fellow at the Max Planck Institute for Intelligent Systems in Stuttgart. It's quite the CV. His interests are in the field of biomaterial science, polymer chemistry, soft matter physics, and nanotechnology, with a focus on exploring biological and bio-inspired materials for healthcare, robotics, and environmental applications. So with that, I would like to pass it on to Abdon, and yeah, floor is yours.
Great, thank you. Thank you very much for the kind words and introduction, and thank you very much for the invitation. I wish I could be there in person and visit your department on site, but especially since I love London. But I'm very happy that even if it's remotely, I can share some of our work with you. So I'm gonna talk to you today about some of our work on bio-inspired materials, and specifically on some bio-inspired polypeptides that we developed with applications in soft robotics and in soft small-scale robotics. So I think you should be able to see the pointer, I think. So hopefully I'm gonna, okay, great.
Yes.
So I like to start by, okay, you can see the pointer, but I cannot. Okay, great. So I like to start by giving a bit of context on the work that we do. If we look at robots today, right, we see that they're pretty awesome, right? They can do very complex and accurate tasks across length scale, right? We see here some examples from humanoid robots to industrial robotic arms to insect scale robots, and they can perform these very accurate and complex tasks. And despite robotics being quite a young research field, there's been in recent years great developments in both the brain of the robot, things like in computer vision, in planning, etc., but also in the body, right? But if we compare this to their biological analogs, we see that we're still quite far in terms of achieving the same level of complexity and adaptation to their environment, right? And especially this is very striking when we go down in length scale, right? When we look at the micro scale and nanoscale, we see that we have very complex, in nature, we have very complex organisms that are able to perform very decision making. They can perform very complex tasks autonomously, right? So this brings many challenges, as we're saying, not only on the brain of these systems to achieve this complexity, but also in the body. We need some physical constructs, right, that can enable all these advanced functions, right? So this is an area that we're very interested in from the material science perspectives. And just as an anecdote, I had this, been using this slide for a while, but when looking at your department website, I saw that you have a similar design on your website. So we have there's some aligned interest in this. So I was very very happy to see that. But going back to that, as I was saying, I'm very interested in developing these new robot bodies, right, or these robot physical constructs that can enable all these functions, right? And this in the road of achieving this biological complexity in synthetic systems, there are many grand challenges, right? And the first one that I would like to bring up is, of course, miniaturization, right? If we think of traditional or classic robots, they're typically made of bulky components, bulky materials, that they're very difficult to miniaturize, right? At some point, we're going to run out of space and we cannot fit all these batteries, all these actuators, etc., right? So we need to come up with new strategies to achieve control power and actuation at small scales, right? Like they did in the Fantastic Voyage, great sci-fi classic from the 60s. But also, and following up on the miniaturization, multifunctionality is a big challenge because rather than having these multiple components that each perform a function, if we're limited in space and we want to miniaturize these systems, we seek for single component systems that can perform multiple functions simultaneously, right? And they can adapt to the environment, they can sense and deform, and can make these decisions and change their properties dynamically on demand. So this is these go tied to hand by hand, and they all come from the same rooted problem in complexity at the small scale, right? And of course, you can imagine if we can make these machines, they will have a tremendous potential for targeted therapy and for non-invasive surgery. But of course, this brings challenges on safety, on not only on operation in physiologically relevant environments and biologically relevant functions, but also biocompatibility challenges, biogradation challenges, and immunogenicity challenges. So when we look at these problems, right, we see that there are many opportunities from classically trained roboticists, but also this opens the door for many other scientists in different areas, like material scientists like myself. So this is a great opportunity for interdisciplinary research, and this is what we do in our lab, right? So we look at nature, we study interesting materials or structures or some biological functions that we're interested in, and with polymer chemistry and soft matter physics, we try to replicate these functions and structures in synthetic systems for to solve some of these emerging challenges in robotics. Right? So in our group, we work on both fundamental science in materials development, but also in applied engineering towards these applications in robotics. And today I'm going to show you a few examples of some of our pieces of work on soft actuators that are self-healing, on powering microrobots, and on biointerface engineering of microrobots to control the interactions with the immune system. So I'll start with the actuators first, because it's a bit more extensive work. When we look at traditional rigid robots, right, we see that they're typically they're very resistant to sharp forces, but typically they're vulnerable to misalignment, to collision damage, to deformations, to impact forces, basically, right? And because of this and this lack of compliance, soft robotics emerge as a solution, right? And replacing these rigid components and rigid materials with flexible and stretchable materials that they can withstand large deformations, large impacts, but because they're inherently soft and compliant, they are vulnerable to sharps, right? And then cut damage, puncture, and tear, they become a big problem, right? And this is a big roadblock for the translation of these concept soft robot designs to real applications in industry and in clinics, right? But we see in nature many different healing mechanisms to repair these damages, right? So we're very interested in taking these properties and functions that are typically attributed to biology and integrated them into our synthetic materials. Luckily, self-healing has been around for a while, right? And there's a great body of work from the polymers chemistry perspective, right? So we can just briefly, as a brief intro, we can categorize self-healing materials, especially polymer-based self-healing materials, in two main categories: extrinsic healing that relies on the addition of an external component, that can be some catalyst, some healing agents, some fresh monomers, etc. Right? Whether it's embedded in a capsule form or whether these are fed through a vascularized system. These have some pros and cons, of course. It's good because they're very autonomous. So once you have some damage, these capsules or these vascular networks are broken, this healing agent is released, and it's very, it doesn't require an external stimulus. There are some limitations, for example, that the cycling, the number of times that you can heal this material is limited, and you need to constantly be feeding these healing agents. On the other hand, we have intrinsic healing mechanisms that rely on supramolecular chemistry and in reversible or non-covalent dynamic cross-linking, right? And we're very interested on these type of materials because the network happens at the molecular scale, right? So you're repairing bonds through different chemistry and different mechanisms, but you can repair very localized small scale damage from small scale damage to macro scale damage, right? So we're very interested in this later type of healing strategies. But this has a problem, right? And we can see here on the left, there's several different examples of intrinsic healing chemistries through hydrogen bonding, through disulfide bonds, etc. But a common challenge to these materials is that if we look in here at this graph that plots the healing strength versus the healing time, we see that there's a fundamental trade-off between those, right? And this comes for if we want fast healing, you need some high chain diffusion and high chain mobility that comes at the cost of stiffness in your material, right? So this leaves this region over here, right, of fast and strong healing quite unexplored, right? And from a practical point of view, this will be great, right? Because you don't want in your device, you don't want long off-duty times where you're losing that function, right? So we're very interested in breaking this trade-off and achieving this fast and strong healing. And to do this, we looked into nature, right? And we look especially into structural proteins because they're kind of our favorite materials, but we're clearly biased. But we love structural proteins because they are very versatile. They have a huge diversity, right? With mechanical properties going from extremely soft to extremely hard tissue, right? We see here many different examples from collagen, from silk fibrin, etc., right? And we're very interested in the self-assembly mechanisms that are driven by the specific motifs in the amino acid sequences of these proteins. So we work a lot with a protein that is found in squid that has been recently discovered in several years. It's called squid sucker ring teeth, or SRT. And this protein, and keep an eye next time you see a squid or you order some calamari, hopefully you'll remember this. You'll see that squids have this teeth structure inside their suction cups that they use to catch their prey. So it's not just vacuum, right, or suction that suction that they apply, but also they have some mechanical attachment to their prey. So these are the rings once you take them out, and what happens is that it's a very hard material. And unlike other hard tissue in cephalopods, these are not mineralized. They're composed of 100% of protein. And we're very interested in seeing how the squid makes this material, where do these extreme mechanical properties come from, and what's its structure, what is its nanostructure. So we looked into different squid species around the world. We see here at the bottom, you have this, you can see that different species have different morphology, and you can see in here that each of these species has a different protein composition, right? And you can see it's quite messy, it's quite diverse, but in all of their cases, these proteins range between 15 and 60 kilodalton in molecular weight. So what we did is we sequence all these proteins and all these across species. And I'm not going to show the full sequencing work because it will take forever. But what I can show you is that because we looked at all these different species, we could identify some common motifs that are repeated across not only these different proteins within the same species, but also across species. So we could, by using bioinformatics and analyzing the amino acid sequence of all these species, we could come up with a master sequence or a master building block that is recurring across species, right? And we'll talk about the sequence here in a second. But what we did then is this gave us the we could use this as a great materials platform to develop a library of bio-inspired materials that can replicate these extreme mechanical properties from squids. And one of the main advantages of using this, this custom bio-inspired master sequence is that we can have a great degree of control over the molecular weight and the sequence, of course. By using, repeating this building block discrete and precise number of times, we can synthesize monodisperse proteins, as you can see in here, right? By repeating this segment 4, 7, 11, and 25 times, that look much better than this mess of the wild proteins, right? So as you can imagine, in order to do systematic study, to develop to look into the sequence structural properties of these materials, this is a much better platform, right? Not only because this is you decrease this diversity and these deviations, but also because you can synthesize proteins that go beyond the range of molecular weight that you see in nature. So you can go beyond that. But also, because of the specific sequence that is recurring across squid species, we can see here that it has like two blocks, right? One yellow and one blue. We can see this blue block is rich in alanine amino acids, which are very hydrophobic, and they can aggregate and form beta sheet nanostructures. And this yellow chain is rich in glycine amino acids that are typically very flexible, right? So when you have these two blocks repeated along your protein chain, this assembles into semicrystalline structures like this, right? Where these beta sheet nanostructures act as physical crosslinks, right? So the main motivation to pursue this work on squid-inspired proteins was how can we use these physical crosslinks, right, to repair the molecular, the damage in the network, right? So we can use this as reversible crosslinks for our healing, network healing strategies. But as you can imagine, this brought a lot of problems. One of the big ones was that when you have a self-assembled nanostructures, you end up with a lot of molecular defects, right? The molecular defects being things like this, like, for example, like dangling ends on some like loops in your structure that are chains that are not really contributing to the material's properties, right? If you can think, for example, in mechanical properties, when you stretch your network, these will not bear any load, any stress, right? So they're detrimental to your structures, right, and to your properties. So this is a long-standing challenge in polymer networks, and it's very difficult to have a controlled network topology, right? So what we could do is by controlling not only the molecular weight, but because of this sequence that has and controlling the size of the nanocrystals, we could we built a model that could predict this molecular defect density, and we could optimize the structures beyond what we find in nature again. And you can see here, this is the cohesion of this property of this protein. Sorry, this red bubble here is what we see in nature, but you can see that by playing with the molecular weight, we can improve the topology beyond what we see in nature and reduce the molecular defect density. So you can see here on the right, these two materials, they have the same, same chemistry, same crystallinity, same everything, except different. They have different network topology. So you can see that we can go from very brittle materials to very elastic ones, right? So these proteins give us a great platform to control and optimize the network topology to have very resilient materials. So once we had this optimized network with optimized mechanical properties, we looked into the healing properties, right? And basically, now that we have a good network without defects, can we repair that that network through the beta sheet formation? And you can see here that it's quite fast, right? In this case, we give it a little bit of temperature. This is around 40 to 45 degrees. We can heal within seconds, right? And although the healing happens at room temperature and it heals within minutes, right? We wanted to show that by just giving a little bit of extra help and to enhance that chain diffusion, we can have very strong healing in the range of megapascals in here. I think around like 20, 25 megapascal for the most efficient networks that we got. But we can achieve this within 1 second, which is great, because we're kind of in this optimal performance space, right? So when we saw this, we were very excited, and we wanted to validate this against different types of damage, right? And we tortured our materials basically. So we validate against different types of mechanical damage. For example, we can see here against scratch, we use the protein as a protective film, where we could scratch the surface, exposing the material underneath, but we could recover after a very short healing time the surface coverage. We tested these against puncture damage. These are, I think these were like 20 micron flexible protein films that we stabbed with many different needles, and you can see how you can repair these small scale hole defects. But also we looked at how the material recovers from complete cut damage into different pieces. And what we're very excited about is that what you can see in here, that this is the area that was the healed area. You can see that when this breaks, it breaks from a different position, which is telling us that at least the healing and the network repair is effective, and that the healed area is at least as strong as the original material, which is great, because it's telling us that this works, right? But so it was great, and we wanted to, especially we got very excited when we saw that we could heal these small defects, and we wanted to see how we can make an impact in robotics for this, right? Because what happens is typically in pressurized systems, which are arguably one of the most common soft actuation methods in robotics, these type of puncture defects are typically catastrophic, right? And as you can imagine, if you have a pressurized system with a hole, that kills any functionality of your device, right? So this is a big durability problem for these type of actuators. So we wanted to test these self-healing materials and in a prototype pneumatic soft actuator. And we developed a very simple proof of concept pocket actuator that consisted in two protein membranes that are joined at the edges here, and when this is pressurized, it inflates, exerting a normal force to the surface, right? And we stopped this, right, to have like this damage and healing, and we didn't see any loss of performance in both in terms of force or in deformation across several cycles of damage and healing. And we tested this in several prototypes, both as a gripper, as we see here on the left, because of the softness and the very thin materials that since this is healing, we can go very thin and not worry about the damage. This conforms greatly to complex objects, such as this is a cherry tomato, but it's tricky to handle with rigid manipulators. We developed a simple but quite cool artificial muscle prototype that can lift many times its active mass and performs quite well. And also, we're very interested in taking advantage of this dynamic cross-linking and this reversible cross-linking, not only from the healing perspective, but also from a sustainability perspective, right? Not only from how can I say, not only for recycling these materials, but also for enabling the degradation of these actuators, especially with field robotics in mind. So in this case, this is a chemical stimulus. This is pH, which is very fast, and we use pH for a bit of drama and to have a fast video. But of course, this can be also enzymatically degraded, and you can control the degradation kinetics for a desired degradation profile. But it was quite good because this, the performance of this, although we didn't shoot for this, right? But this turns out that because you can make them very thin and not worry about these damages, you can make it quite small. So you can get quite this pack a punch for the small footprint that they have. But we're more interested, rather than targeting specific metrics, we're interested in enabling different new functions, right? And one thing that we're very interested also is on applying these protein-based and bio-inspired materials to different types of actuation, right? And we're developing this very recent work from my student Zane. We're making soft magnetic composites that we can use as a smart material that can deform on demand, right? So if you can control a specific internal magnetization profile in your material by controlling the arrangement of micro and nanoparticles, when you expose it to an homogeneous external magnetic field, you will get torque-driven actuation in there, right? So torque-driven bending, sorry. But what happens is once the magnetization is set, right, you can rewrite the magnetization, but it's hard to rearrange the particles inside the material, right? So we wanted to use these healing properties to kind of reconfigure our materials so we can achieve very complex magnetization patterns that allow us to have some complex actuation modes, right? And we can change it and rearrange on demand, as we can see here. So we can have opposing ends from the same piece. So this allows for on the spot rearrangement of the robot, in this case, this gripper modes of actuation. So this is still very recent work. We're still working on it, still unpublished. But this is an area where we can see how these protein-based materials can not just make good soft actuators, but can enable some other functionalities that conventional elastomers don't have. Another example that I wanted to show you, right, and moving on to the second piece of work that I wanted to share with you. This is related to how we can power these robots at smaller scales, right? And this is a challenge because when we look at at motors, right, at the macro scale, we think of electric motors, combustion motors, etc. Right, but these are very difficult to miniaturize, right? Because we cannot just take one and make it smaller, right? Because they have a lot of moving parts. It's very complex to miniaturize. So the macro scale, the micro robotics community has come up with many different types of actuation, right? You can see here a few examples using acoustic propulsion, magnetic actuation, or chemical propulsion, right? So we could talk about this for hours. Each of these have their own pros and cons, but for the sake of the presentation and for just because we have limited time, I wanted to focus on chemical propulsion, right? Because it's quite good, because typically you can use, it takes advantages from chemical reactions or some fuel that is entrapped in the robot body. But the problem is that typically these rely on the generation of microbubbles, and typically this needs some aggressive pH conditions on some nasty and hazardous chemicals like hydrogen peroxide, hydrazine, etc. Right? But if we look at nature, again, we see that we have plenty of examples of chemical motors, right, across length scales also. And we're very interested in semi-aquatic insects because they have very cool propulsion and locomotion mechanisms, right? Specifically, this little guy over here, this comes from a family of insects, right? Mesovelia and Microvelia, that they secrete this surfactant, and they float on the surface of water. But when they need to run away from predators, they dip it in the water, and they because it's a surfactant with very low surface tension, when it touches the water, it locally decreases the surface tension, generates this very anisotropic surface tension gradient around the insect, which generates Marangoni propulsion forces, and they go really fast with it, so they can escape from the predators. So we wanted to take this concept and integrate it into our robots, right? And for this, we used the same protein material from the squids that we were talking about very recently. We used these proteins as the motor matrix, and we infused it with HFIP, hexafluoroisopropanol, as a fuel, right? This is a very volatile, low surface tension solvent. That what happens is, it dissolves this protein, and also it blocks the formation of these beta sheet nanostructures. So when we have this material, you can see here in this schematic, you have some amorphous material embedded with this fuel, and as soon as it comes in contact with water, this fuel is released, and as it's released, you start seeing the reformation of these beta sheet structures, right? So it's a kind of an exchange between fuel contact and crystallinity in your material. So this is great to help regulate this release of the fuel, and the whole point of this is you can fabricate some microstructures from this motor material, this protein. You can that has some anisotropy. You can generate this anisotropic surface tension gradient that will give you some Marangoni propulsion. And we can see here, I think, okay, it froze for a second. So we make this like arrowhead design for control motion, but you can see that they can move pretty fast, and we can scale down the designs across length scale. We can go down to the micro scale, as you'll see, in the videos, how we going down. So these move very fast, and they can achieve. They can move for long distances over long periods of time, right? So these show great performance compared to similar type of motors. But again, what we wanted to do is explore some new functions that other materials don't have, right? And because we can dissolve this protein and cast it, and it's very versatile in the fabrication, we can also embed some drugs for cargo and drug delivery for this, right? So as you can see here, we have these little motors spinning around, but loaded, in this case, this is with a dye, but we loaded with dogs and with some other molecules just for testing. But you can control their locomotion by giving some external stimulus. In this case, it's pH that can open up the porosity of the material, right, by breaking these beta sheet interaction, these beta sheet structures. So you can open it up so this dye is released over time, so you can use it for controlled, on-demand stimulus-responsive delivery of many molecules. But also one area that we're very interested in, or that we're working on right now, is that because the processing of this protein is very, very versatile, so we can use it as a paint, right, as a functional coating to propel and to power inactive materials, right? Think if you have a canoe and you go to the to the Thames, and you don't want to row, you paint your boat or your canoe with this motor paint, and it will propel you down the river, right? So of course it won't work at that large scale, but it works at the centimeter and below scales, right? So you can see here, this is just a piece of laser cut piece of I think it was PET or some random material, right? But we can coat these materials and give them this kind of modular power source. But what we're very interested on is on combining these modular power sources with already existing micro robot designs. Like we can see in here on the right, this is a magnetic micro robot that we can control by using external magnetic fields, right? So rather than using magnetic fields for propulsion, we're using it for steering. And we're using these chemical motors, these protein coatings, as a modular power source. So this is very appealing because we can decouple then both steering and direction control from propulsion. So you can have a much better control and much better functionality in your robot design. So this is an area that we're very interested right now. This is some work done by my students Chahan and Cecilia. And also last, I think we're doing okay in time. I think I wanted to show you some of our recent work also. This is on the third big challenge that I talked earlier, right, on the safety and on the interaction of these robots with the body, right? And as most of you, I'm sure you know, right, there's many problems with barrier penetration when you put anything in the body, right, from any implantable materials, any nanoparticle platform, etc. Especially when it comes to immune recognition and immune clearance, right? Because and the same thing happens with micro robots. And it doesn't matter how fancy your nanoparticles are or your robots, if they're cleared by the immune system, they will not reach its target, and they will not perform their main function, right? So there's a huge loss in functionality that you need to compensate by increasing the dosage, right? So we're very interested in this problem, especially because at the root of this immune recognition, there is a biofoiling problem, and most most people use PEG as a gold standard anti-biofouling material to prevent the absorption of the non-specific absorption of plasma proteins, for example. And this is great, and it works okay, but it has some problems, right? So the anti-biofouling properties of PEG rely on a good grafting density. They rely on mechanical agitation, and we're starting to see already some anti-PEG antibodies, right? So they work good, but not great, right? So this limits a lot the protection of these PEG coatings for immune recognition and immune clearance and absorption of proteins. So what we did is with my student Paul. He was a student when I was the Max Planck in Germany. We developed a library of deuterionic polymers that, in case if you're not familiar with the term, these are polymers that have both positive and negative charges, but an overall zero net charge, that are inspired in the different protonation states of natural amino acids, right? And we developed deuterionic hydrogels that are very hydrophilic, that have zero net charge, and they have a thick hydration layer that prevents the absorption of these proteins that trigger the immune recognition in most systems, right? So what we did is we made not just a library of different monomers, but also fully deuterionic cross-linkers to develop deuterionic photoresists for microprinting, right? So you can see here, we designed these helical robots, and I'll talk about this helical shape in a second. But we use these deuterionic materials to 3D print these fully deuterionic micro robots. And the reason for this helical shape is that we're using this shape for magnetic actuation. So during the printing process, we embed spion particles, super paramagnetic iron oxide nanoparticles, and we use rotating external magnetic fields to rotate these helix. So we're literally drilling through the fluid at low Reynolds numbers, right? So you can see we can get controlling the field and the frequency. We can get different types of locomotion, and then we can encapsulate some other drugs for targeted and on-demand stimulus responsive delivery of therapeutics. But what we were more than in this, we're very interested in seeing how these deuterionic polymers behave when in contact with immune cells, right? So we co-culture them with macrophages and with splenocytes, and you will see here there's a big difference from PEG-based microrobots here on the left, which is the current gold standard for anti-biofouling materials, and our deuterionic microrobots here on the left. So you'll see that as soon as the macrophages come in contact with I hope the video can play well over Teams, but you can see that as soon as they come in contact with the microrobot, they're captured immediately. While with the deuterionic microrobots, you can see that they don't. Right? You can see that the macrophages are inspecting them. They know that something is there, but they're really not triggered and not attacked by the macrophages. So we can see that there's no phagocytosis over many hours, up to 90 hours of co-culture with these robots. And you can see here that even in some of them, they're exhaustively inspected but we don't see any recognition from the and uptake from the macrophages. So this is an area that we're quite interested also, because this is a big big roadblock for developing new micro robots that can that can operate safely in the body. So we're very excited about the potential of these new materials for microprinting and micro fabrication in general. And with this, I would like to wrap up. Just as a big picture, a summary of the things that we do. Again, we take inspiration in nature to see some properties or some nanostructures that can give us cool functionalities that we can apply in robotics, and then we study their structure and try to replicate their function at the materials level to expand it and to bring solutions to these applications in robotics. So what we have seen today is that we developed these squid-inspired polypeptides that have an optimized network topology, a network structure with beta sheet physical crosslinks that have very fast and strong self-healing properties by the formation of this nanocrystalline structure. And we used it to develop these self-healing actuators for both pneumatic but also magnetic actuation that can not only enhance their durability but also enable new functions and new modularity in their actuation modes. And also we've used these proteins to develop the self-powered motors by using chemical fuel, and we can use it as a modular power source for other types of micro robots. And just last, we have developed these amino acid inspired zwitterionic polymers to have these micro robots that can evade the macrophage recognition. And with this, I would like to, of course, thank my research group. We're quite a young group. We just started like a year ago. So part of this talk is some work that I did during my postdoc and some work that we're doing here in the lab. But this is the best part of the job, that you get to work with the coolest people. So of course, thanks to my students. I've shown here some of the work by Zane, Cecilia, Chahen, and Paul. And also like to thank Huiwen Jung, and especially Malik Demirel and Metit Siti, who are my PhD and postdoc advisors at the Penn State and also the Max Planck Institute, and also our funding sources for the supporting our research. And of course, thank you all for your attention, and I will be happy to take any questions. Thank you very much.
Thank you very much, Abdon. That was really clear. It was really nice talk. Thank you.
Thank you.
We do have 3 questions in the chat, and if anyone has any other questions, please feel free to put them in the chat. And so the first one is from Chris, who is asking, with regards to your pocket actuator and more in general, how do you stop the material from sticking to itself and forming a blob rather than a structured material?
Okay, sorry, let me open it really. Whoops. Okay, sorry. So material for sticking to itself and forming a blob rather than a structural material. Yes, so that's a good question. And it was a bit of a nightmare to design on the early prototypes. It is a matter of kinetics, right? So what happens in that case, we use some, if you remember from the previous slide, I think I can maybe go back to it. Maybe that might be maybe 17, slide 17. No, that's not slide 17. It's slide, well, I was off for a lot. This is a matter of kinetics, right? If you remember in here, right, in, what is this thing in here? We can get very fast healing by applying a little bit of heat, right? Just above, just room temperature, right? 40 degrees is not too bad, right? So what happens is the healing at room temperature it happens over a longer period of times, right? So we can just selectively hit the damage area and not hit up the rest. So we can have an homogeneous, not an heterogeneous heating and healing of the structure. If you put everything in an oven, for example, then you will get a blob, and those two membranes they will stick together, right? Which they will be maybe. Okay, yeah. So these membranes they will stick together, right? But that's why a spacer here is helpful, and also keep in mind that this is pressurized, right? So this won't be a problem unless you're sucking all the air and you're compressing these two membranes together for a long time. But that's a good question from a practical point of view.
Okay, so the next one, I'll just read out loud for everyone else. If your structures get stronger when they heal, for example, when the system is knocked apart, afterwards it breaks at a different location, does this change the Young's modulus or stiffness, and hence do you need to take this into account when using the healed actuator?
Yeah, that's a good question. It does change a little bit, so it stiffens a bit. How can I say? It's similar to when you have damage in your body, right? You get a bit of a scab, right? And it's a bit of a stiffer tissue, right? So something similar can happen here. This happens because you can, depends on how you heal them, right? And it's a bit, we're cheating a little bit by giving this extra heat, so we can kickstart and really speed up the healing process by creating as many beta sheets as we can. So that increases a little bit the Young modulus, right? But you can, if you just let it heal on its own over a longer period of times, minutes rather than seconds, then you shouldn't have this problem. But in any case, we didn't see that much changes in the performance for this, because keep in mind that for this you start seeing that big difference in modulus when you are stretching it at large strain, right? Keep in mind that in here, right, since you are applying this, you're pressurizing and you are bending, not really stretching that the membrane, it's not that critical. But that's a very good point.
So there's another question from Majid. And also, if anyone else has a question, can we just post it in the chat that you can all unmute yourselves now and ask if you want to. But Majid is asking, I will say, thanks for the inspiring talk. Is it possible to drive more than one magnetic robot in different directions at the same time, given that they're all affected by the magnetic field?
Mm-hmm. Thank you. Thanks. That's a good question. And I have to say, regardless of the question, I think I was yesterday I was giving a class to I have a class on soft robotic actuation, and I was I shared your paper on the I forgot the name. I think it was like this, the electric liquid zipping actuator stuff. So we discussed your paper in class yesterday. So I'm very happy that you asked the question now. So to give an answer of that, you can control in different directions, but it all depends on how you can create that magnetization in your robot, right? It's quite complicated because at that scale you need to be able to print something that will react differently, right? So that the same magnetic field will generate a different hydrodynamics that are going to be in a different direction, for example, right? But having it in different directions is very complicated. What you can do, rather than using the same magnetic field, and it's something that has worked better, is have robots with different magnetic properties, right? So each of them have a different magnetic field threshold, right? So you can have different, for example, step-up frequencies or different susceptibility to magnetic fields, so you can address them individually, right? So this is quite of a active area on control of multiple, robots and swarms, right? So it's quite challenging. But yeah, but with our design, we didn't. We just wanted to see that we can make them swim, but we're more interested rather than in their locomotion in what was the interaction with the immune cells. But that's a very good question. Yeah, thanks.
Wonderful.
Good, thank you.
So, does anyone else have any other questions? I mean, we're pretty much at the time, so I was, yeah. If nobody else has any questions, we can chat later. I'm done.
Okay.
But yeah, cool. Thank you so much, Abdon. That was a really good talk. Very interesting, and yeah, thank you for your time. Thank you for the talk, and thank you everyone for attending.
I wish I could be there in person, maybe sometime in the future to visit your department. But it's been my pleasure. So thank you very much for the invitation.
Wonderful, awesome. All right, thank you.
Good. Thank you very much.
Thank you, Majid.
Bye.